Hello everyone. My name is Morgan Cole, and I'm a rising junior undergrad at UC Berkeley. And I've spent the summer working under the mentorship of Alexander von Anglin and Matthew Matavashvili. I think his name got cut off. And I have been looking at the relativistic effects of the CMB and trying to figure out what that can tell us about the properties of galaxy clusters. So what you can see here is that famous baby picture of the universe found in the microwave frequency sky. And you can also see me in that picture. I was very excited to see this exhibit at the Natural History Museum. And so what that actually is the cosmic microwave background, or the CMB. And that's the very radiation that was produced during the Big Bang that we can still detect today. So while it has taught us a lot about the origins of our universe, it actually can do a lot and help us learn a lot about our more modern universe. So here's an example of that. This is a map of the CMB created in the last few years. And if you were to take a really close look at it, you would notice that there's certain places where the CMB seems to suddenly drop in temperature, and you get these cold spots or drop in intensity. And what we've now found is that those are galaxy clusters. So not only has the CMB provided this really great way of detecting galaxy clusters, but we can actually learn a lot about their properties from it as well. And that's what I'll also be talking about. So in order to understand why you get cold spots on this map of the CMB where there are galaxy clusters, you kind of have to take a look at the thermodynamics. So what's going on here is this process called inverse Compton scattering, where these hot galaxy clusters contain these high energy electrons. And those electrons will excite CMB photons up to higher frequencies. So if you look at the graph over here, that blue curve represents sort of the normal intensity spectrum of the CMB. And the red curve is showing what happens after that scattering. So it shifts to the right to higher frequencies. But if I'm measuring the CMB at this, say the frequency of this purple line, I will observe a drop. I will observe this deficit in CMB intensity. So that's why you get a cold spot, even though things are heating up technically. And that is actually a very well-studied effect known as the Senyaev-Zeldovich or SZ effect. And this is an equation describing that process I just went through. I guess what's important to note here is that variable TCMB, that's the temperature of the CMB, a constant of about 2.73 Kelvin. And this equation depends uniquely on frequency. So if you're looking at this graph below, this blue curve showing the pattern or the growth of f of x, and you may notice that at about 220 gigahertz on the x-axis, it reaches a value of 0. So what does that mean physically? What is the theory trying to predict here? It's basically saying that if you're measuring the CMB at that frequency, you won't see any change in temperature at maybe where you were previously seeing a galaxy cluster. And as you can see in these images I created, that is exactly what happens. So these are all of the same cluster, but measured at the 3 different frequencies. So you see it get a little bit smaller in that second image, and then by the last one, it's basically gone. You don't see that temperature drop at all. So this is a very real effect, and the theory holds up. So that's nice. And then the other part of that equation you may have noticed is that parameter of y, that's called the Compton y parameter. And what's important to point out is that it depends on pressure. And that kind of gets at why the SZ effect is so useful for cosmology, because if you can figure out the way in which the temperature of the CMB has changed, you can figure out the pressure of those galaxy clusters, which can tell you a whole lot about the way those galaxy clusters have formed and evolved. So that's really cool and really useful. But what if there's other things you want to know about galaxy clusters? For example, I'm interested in finding out what are their temperatures. Is there a way to measure that? And in order to figure that out, I need to take into account the relativistic effects of the SZ effect, or the RSC. So I need to factor in special relativity. And the reason I do is because those high energy electrons I mentioned earlier are approaching the speed of light. They are approaching relativistic speeds. So what you're going to see is going to be different than just what those equations were previously predicting. So if you can sort of focus your attention on that yellow curve, that's representing the sort of normal thermal SC effect. And those green curves are showing what would happen if you factor in special relativity. So you see an obvious difference. And if I'd be able to detect that difference in the real data, then I could get direct information about the speed of those electrons and then therefore the temperatures of those galaxy clusters. So that's kind of the ultimate goal, is to get a reasonable detection, a reliable detection of the RSE effect. But it's obviously not that simple. It's not so easy as comparing theory to reality, because there's a lot of things that can create those differences, such as dust and noise. So a big part of my project has been understanding how much those differences are playing in and what's contributing that. Another challenge is that the RSE effect is very small. It would be hard to measure in the first place. So in order to get a good reading on it, I would need very precise measurements that would come from highly sensitive equipment, and that equipment would need to be able to produce high resolution data. So that's why it's been so useful to use data from ACT, or the Atacama Cosmology Telescope, which I'm sure many of you are already familiar with, but for those who may not know, ACT creates maps of the CMB that cover over half the sky at 90, 150, and 220 gigahertz. And the maps it produces have arc-minute resolution. And that uncoincidentally corresponds with the size of galaxy clusters on those maps. So that's what makes ACT so well suited for studying the properties of galaxy clusters. And in the most recent ACT data releases, approximately 4,200 galaxy clusters were detected. And that's what you're seeing in that beautiful scatter plot there. So that's what I've been doing my analysis on. So like I said, a lot of what this involves is understanding other sources of error and uncertainty and quantifying their contributions. So one method I've been using is called stacking. And it's essentially taking multiple images of galaxy clusters, overlaying them, and taking their average values. And so that's what you can see happening in these graphs. The image on the left, pre-stacking, it's a slice of a galaxy cluster. So it's sort of a side view of that cold spot. And that's just a singular galaxy cluster. But then what you see post-stacking is when I take the average of about 30 clusters of similar mass. And it looks a lot cleaner, a lot less randomness. So that's something that's really helpful. But obviously, if I have some noise or error that's affecting all 30 of those clusters, averaging them isn't going to eliminate that. So the other method I've been using is aperture photometry. And my mentor had a great way of explaining that. He had a great analogy, which is if you were imagining trying to see the moon in the sky and it was covered by clouds, something that you could do to sort of isolate the brightness of the moon would be to create this red circle, as I've drawn it, that contains the moon and some of the clouds around it, and then draw this bigger blue circle and create this ring around that that only contains the cloud. So if you could get, say, the average value within that ring and the average value within that circle and subtract their difference, you've basically isolated the contribution from the moon. And so that's analogous to what I've been doing with the clusters and noise. So I take this aperture and I get this average noise value, get this average cluster plus noise value, take their difference, basically cluster plus noise minus noise equals cluster. So that helps to eliminate some of that large scale noise, and that's also helpful. So these are the primary results I've created over the last 2 months. You see this blue curve representing what the theoretical predictions of the SZ effect would have been, and the green curve representing what I actually measured from the data. So they follow similar growth behavior, which is nice, but there's an obvious deficit in the actual data. It doesn't quite reach it. And the uncertainties on that don't account for that difference. And that's actually something my mentors and I are still trying to understand. We don't really know why that's happening. So that kind of brings me to what my next steps will be. We'll continue to look into possible sources of error causing that. We'll refine our uncertainty calculations to maybe be able to account for that difference as well. And something else I hope to incorporate is being able to include higher frequency data, because I'm limited with a maximum of 220 gigahertz right now. So I want to be able to increase to higher frequencies, which would be something I could do with the Planck satellite data. So I plan to incorporate that in my studies also. So hopefully with all of that, I can actually get a reliable measurement of the RSE effect and be able to take these temperatures of these galaxy clusters. So thank you very much.
Yeah. So what is causing that, or what are some potential causes that you and your mentor think could be causing that inflection point at about 150 gigahertz for the data?
Yeah, so it's a little bit deceptive because where it looks like it's differing from that is based on how it's fitted. And
Oh, I
so
see.
you could fit it so that it does match at that point.
Hmm.
But this consistent deficit, there's a lot of possible sources of error. We're still suspicious that it might just be within our uncertainty calculations and that it's something we can account for reasonably. But something we're going to do next is actually do this basically the same process, but in bins of different masses. Because something I might have forgot to mention earlier is that those more massive clusters will have hotter, faster electrons. So you'll have more of this relativistic effect. And so doing it in different tiers of mass can reveal if that difference is what might be causing this.
Cool. Thank you.
When you do the stacking,
Yeah.
you're stacking different clusters on top of each other.
Mm-hmm.
So then if you were able to measure the temperature, that would just tell you that, would that just tell you the average temperature of those 30 clusters? Is that right?
Pretty much. And 30 is a small number. That was sort of just for demonstration. Well, actually, that was the top tier mass clusters.
Okay.
But yeah, that was something that was hard for me to sort of settle with is you're not going to maybe, it's not really like taking each individual cluster's temperature because the RSC effect is so small. You're not going to see it unless you combine a number of different clusters. So you'd get a good overall summary. You could say, oh, you know, clusters of approximately this mass or some other characteristic have this kind of RSC effect.
Yeah. So in systematic uncertainties, there's three sources typically. There's something about nature we're not understanding, something about our instrument we're not understanding, something about our data analysis process. So, what do you think is happening here? If there's a system, if that's due to some systematic uncertainty, where do you think it may lie?
Well, the prime suspect is the data and the analysis itself, is how we're calculating this uncertainty. So the way we've been calculating it is based on the aperture photometry methods. So it could be something within that. It could be, there's many different ways to do that with different radii and stuff. So we hope to explore different ways to do that. And then from there, we would start to see, okay, well, is it a different source of error other than this correlated noise? And then I think, I don't know if it could be something bigger than that, but that would be cool too.